This is the breakdown video of my PCG Endless Runner game. So to start off, I'm just going to show a little bit of basic gameplay. So when you start the game, you'll find yourself in a main menu. There are two buttons here because I have two different game modes. Endless mode is quite self-explanatory. It's a mode where the path will spawn forever until the player dies. The game will just keep going until the end condition is met. Adventure mode, it takes the same Endless Runner concept, but it splits the path up into rounds. So after a certain amount of time that the player has been running for, the level will change. They'll find themselves in another level called the Plaza, and in this place they can generate quests and they can purchase rewards using coins they've collected. So I'm going to show endless mode for now, just so the path generation can be shown. You're taken to this new level, which is the endless running level. And as you can see, all of the mesh spawn in. There are coins along the track. They bend around obstacles, as you can see. The player just needs to avoid all of the obstacles around them in order to progress. There are also power-ups. Yeah, that's some basic gameplay for now. When the player hits an object, they'll fall and die. And then after that, you're taken to a death screen, which gives the player some statistics, so how many rounds they've completed, their score, and the coins they've collected. So now I'm just going to show a bit more of the path generation. So I'll go to the level where the path actually is. So this is the Endless Runner level. As you can see, it's completely empty to begin with. There are no actors, no meshes, nothing, because everything that is part of the gameplay is procedurally generated. So if I simulate the level right now, you can see the path being created. So the player would start here. I decided to start the game with an empty piece of path first, so that it wouldn't be too immediately difficult for the player when they start. So they'll start on this empty path, and then once this piece is finished, that's when the rest of them start spawning, and you can see the coins and the obstacles throughout. So there are different floor pieces of different lengths, as you can see here. This is an extra large one. And then on either sides of each floor piece are decor pieces. These have to match the length of the floor piece exactly. Otherwise, when they spawn, they'll get completely out of sync. So these floor pieces are also extra large. These sizes are marked with an enum that I created. And when they're generated, they're checked against one another to make sure that they match. This is the same all floor pieces, so these are extra large. We have small ones here. These are also small ones. This is a medium one. And yeah, it just continues like this the whole way through. So the main thing that's interesting about how this is generated is that the generation, the path will be different every single time. So you can see here, we've started this time with two extra large floor pieces, or decor pieces. We've got the settlement piece on this side, and then on the other side, we have the river piece, and then that's followed by 4 smaller pieces. Then if we stop the simulation and we run it again, it's completely different. So this time there's a lot of extra large pieces that have spawned. They continue until here's a medium piece that spawned. Then we've got 2 small pieces, another extra large piece. And then I'll just stop it and I'll run the simulation one more time to prove the randomness of the generation. See, this time it starts with some medium pieces. Quite a lot of medium pieces. Then it goes to an extra large, then more medium, a small, more extra large, and it continues. So as you can see, they're all the different decor pieces are decorated in different ways. Most of them are fairly simple. It took a little bit of trial and error to get things to spawn exactly how I wanted to. But my main goal was to try and make them all seem thematically similar while keeping a difference in appearance that would make the procedural surroundings seem varied enough to keep the player from feeling bored. The most complex decor piece I have is the river piece, which there's an example of one here, because you can see here the river follows a spline. The spline is procedurally generated, so the rivers on the pieces are different every time. So how it works is there's an origin point of the spline in the center here. This is all that exists by default. After that, the program will decide that we'll use a for loop to pick a number for the number of points the spline should have, which will determine the length of the river. There's then another number that is generated to determine how far apart the points should be. So for instance, these 2 points are much further apart than these 2 points. This is decided by the program. And additionally, there's another number that will determine the angle of the next point. So it's clamped within a 30-degree range, positive and negative. So for instance, if we choose this point here, the next point could only go 30 degrees either way of this point. This is so that the spline can't go back on itself, otherwise the river would be overlapping itself, which wouldn't look natural and it wouldn't look right with the surroundings. So this took a bit of work to get working correctly, but yeah, that's the most complex piece there is. Now on to the runner itself. All of the obstacles that you can see placed along the path, these are also procedurally generated. So no floor piece will be exactly the same with the obstacles that are spawned. So here there's a log, there's a rock, and there's some vines. This is on a medium piece. This is also a medium piece. We've now got a log and a rock next to each other, a tree stump, and some vines at the end. There's also a deer here. The deer are the most interesting of the obstacles because unlike all of the others, they move. So they'll spawn on their spawn points like all of the static ones, but they will then move forwards towards the player so that they can run into them, which just adds a bit more challenge. So how the spawn points work is the program will look at the enum for the size of the segments. It will then decide how many spawn points it needs to generate based on the length. So for instance, a small section wouldn't need as many spawn points as a large one because there's just no need for it. There's no room. It could be overfilled with obstacles and just be too difficult to complete. So once it does that, it will create arrows at these locations, and then it will add all of these arrows to an array, and it will then choose from the array which one should spawn an object. And then it just chooses a random object to spawn at these locations. There's also a chance that it can choose to, instead of spawn an obstacle, it can choose to spawn a pickup. Let's try and find one. Here's a shield. So I've weighted these so that it's much less likely that a pickup is going to spawn than an obstacle, because I want them to be rarer, because otherwise the game would be too easy. You can't have too many pickups, otherwise there'd just be no challenge. So these are used to give the player a little boost. So the shield will allow the player to not take any damage while it's active if they run into an item. I also have a magnet. I don't know if one will spawn. There's one. Which will, if the player collects it, they will start drawing coins in towards them, as if the coins have been magnetized to them. Both power-ups last for about 5 seconds, and then they disappear after that. The other collectibles present, as you can see, are coins. These can be collected by the player, and they will then be used in the plaza as currency to buy rewards. As you can see, they also bend around obstacles. I did this because I didn't think it would look particularly realistic if the line of coins just went straight through the obstacles. So the way I did this was I added some splines to the floor pieces. I then got the length of the splines, found how many points there were, iterated through the number of points, and for each point I fired a line trace downwards, and then if the trace hit an object, it would offset the coin's position on the z-axis to account for the obstacle in its path, which is what makes them raise if an obstacle is in their way. This was quite difficult to get working at first because any change in collision by accident would mean that it just didn't work. If the splines didn't have enough points, it just wouldn't work. So there were a lot of things that needed to be fine-tuned with this system, but I think it's quite effective in the end. So I'll just do one final generation. Another thing that's interesting, it's difficult to show with the player like this, because obviously, while it's being simulated, the player is moving. If they run into an object, they will just die, but nothing will remain in the level for very long. So as soon as it's no longer relevant to the player, as soon as they can no longer see either the floor pieces they've been on, the obstacles they've passed, the decorations around them, once they're far enough ahead of them, these pieces will be despawned, they'll be deleted and destroyed. This is so that the program isn't using up too much memory space, because since pieces can be spawned forever, you could potentially end up with thousands and thousands of floor pieces next to one another, which eventually would slow the game down so much it would be completely difficult to play. So as soon as the pieces are no longer relevant, they will be despawned to preserve performance. The next thing I can show is the plaza area. So this is only accessible to the player if they've chosen to play in adventure mode. This has its own PCG system. So there's a floor here, and then the surroundings are all generated to be ignoring the floor. In here, they'll be able to choose quests from the quest board and rewards from the reward chest. So if we start the game again, I can run it on adventure mode, and we can see the player breach the plaza and decide what to do. So as you can see, the player reached a certain point in adventure mode where the screen faded to black and they started moving forwards on their own. I also cannot control the player once they're in this state. After the screen fades to black, the player finds himself here, which is the plaza. This is where they can choose the quests and their rewards. So this is the quest board. If a quest is active, it will show up here. Currently there is no active quest, so there's nothing here. To get a new quest, you have to press the new quest button. The text comes up here. There are two types of quests, jump quests and coin collection quests. The numbers being chosen are based on variables in a struct, which are helped to determine what the quest will be. So this number is different every time. The number is also dependent on the difficulty factor for the quests. So the number of rounds that you've completed in adventure mode will make the quests that can be generated more difficult. So while at the moment the coin collection quests only seem to go up to about 130 coins roughly, but are mostly around the 60 to 70 range. Once more rounds have been completed, the coin amount to be collected can reach numbers such as 300, as is currently set. This number can be adjusted by anyone. So if anyone was going to use this project as a tool to create their own endless runner, to adjust the quests, it's as easy as changing the numbers in the struct. So to accept a quest, you have to press the Accept Quest button here. Fuck, I never... This is the rewards chest. Player can spend the coins they've collected here to get upgrades. The coins that they had to spend are shown here in the top corner. So in the last round I collected 118 coins, which means I have that many to spend. The names of the power-ups are shown here, their cost is underneath, and the choose button is below that. So currently, I can't afford to buy any rewards. See, if I were to choose the increased score multiplier now, it would tell me, you cannot afford this reward. So I'll have to come back once I have more money to spend on rewards. To resume the gameplay, you press the door and you're transported back to the Endless Runner. It shows at the top that the round has changed. We're now on round 2. As you can see, the score is carried over from last time, as is the coin count. And now, the quest text of the quest that chose is displayed on the screen. So now I'm going to force a quest completion event. The problem with a procedural system such as this one is that it can be quite hard to showcase some mechanics because of the random nature of the program. So I've turned off the collision in adventure mode, well, the damaging collision, so that the player can't die. And I'm going to choose a coin quest with a relatively low number of coins to collect. This should be fine. We'll then go to adventure mode, complete the quest, so that I can show what happens then. So as you can see, the quest has now been marked as complete because 67 coins have been collected. So we'll now just keep going until the round changes, which it now has. It looks a little strange there because of how I've had to force things. So we're now back in the plaza. We can now generate a new quest, such as that. Now that a quest has been completed and a new round has been completed, you can see that the numbers that can be generated for the quest are a lot higher. So where before the highest number we were seeing being generated was around 130, now that another round has been completed, or in this case where I've had to force it, 2 rounds have technically been completed, the number can go up to at least 226. So that shows the difficulty weighting a little bit. Then if we go to the reward chest, we can see that it says here that rewards are 20% off. This is because we were able to complete the coin quest we were just given. So when a quest is being completed, it will give the player a discount based on the difficulty of the quest. Now the quest we had last time was quite easy, so the discount is only 20%. The quest that we just accepted, one with a lot of coins to collect, that would provide a much higher discount to the player. So normally, for instance, the double jump costs 10,000 coins. Now with the 20% discount, it only costs 8,000. We of course still can't afford any of them, but they are discounted due to the reward completion, the quest completion. I chose to include this because it gives the players an incentive to actually choose and complete the quests. If the quests were there but there was no real benefit to doing them, players wouldn't choose to do them just because there'd be no point. So this is to sort of incentivize the players to keep going. I'm now going to briefly show some blueprints that I've used for the project. So this is in the game mode for the Endless Runner. This is the event graph. This is all connected to begin play. So at the beginning, there's a lot of functions used to set variables. So for example, if this is the second round in the Endless Runner in adventure mode, and we need the score and the coins to come back, there's a lot of calls to the game instance where all of the information is saved so that it can be accessed again in the Endless Runner. Also, all of the UI is set up, the movement, there's just a lot of things set up over there. After all of that is done is when the floor generation begins. So this is still on begin play. The user will choose how many floor tiles they want to have present at one time. I've currently set it to 15. This can be useful if the designer wants to maybe move the camera, change the angle of it. Obviously, a different camera angle may mean that they're able to see more of the world around them than is set up in mine currently. So they may need more floor pieces to cover up the empty level. Alternatively, their camera might be a lot more closed in than mine is currently, and so they wouldn't even need 15. So to improve performance even more, they may keep the number to something else smaller, like 5, because that's all they'd need. So you pick the number of tiles, it then minuses 1 for the for loop. It will then, in the for loop, it will choose a length from this array of enums. So you can see here, I have set up small, medium, and extra large. These are the current sizes of the floor pieces. I explained earlier how this is attached to things like the number of obstacles that can spawn, syncing up the floor pieces and the decor pieces sizes. So it picks a random length. It then sets it. Then over here, it's the length that has been chosen is passed into some more functions. So we've got add floor, add right decor, and add left decor. These functions essentially do the same thing. This is obviously for the floor, and these are for the decor. These, unfortunately, couldn't be part of the same function because of the different spawn points they need to have. It's easier to have them separately. If we look at the add floor function as our example, in here, we have the current section length. We then have an array of floor pieces. So this is where everything is contained. So we've got the floor parent, the floor medium, and the floor extra large. These are just the different sizes of floors. So if we were to go into the right decor array, for instance, you can see there's even more. That's because there's more types of decor piece than a floor piece. So we've got the trees, the clearing, the river, animal, settlement, and field. So it will shuffle this array of floor pieces so that it's in a random order each time, and then it will start a for each loop and iterate through every element in the array. It will check each one that it passes to see whether it's the size of the current array index matches the length that the program has already chosen to spawn. As soon as one does, it will get the attach point and spawn the chosen floor piece at this location. It will then get the new attach point of the new floor piece, set it to a variable, and add the floor piece to an array of floor tiles. This is to keep on top of the ones that are currently present in the level. Once there are 15, as was my set number, ones at the beginning of the array will start to be removed. So as one is added, one will be removed. This will keep going. So this function is pretty much the same in the decor pieces. It uses the same section length so that it will sync up. And yeah, it's essentially the same thing. So this will happen until the for loop in the event graph is finished. This is just to set up the initial 15. So for example, you can't have at the beginning of the game, you can't just spawn pieces one at a time because there isn't enough. The player would eventually fall off the stage, or it wouldn't look like the path was endless, it would look as though it was spawning in front of them, which isn't the sort of look that the project aims to achieve. So after this for loop is completed, the floor spawning functionality actually goes to the floors themselves. So in the floors, there is this collision box at the end. When the player passes through this collision box, a very similar function to the ones in the game mode are started, where it will choose a floor length and then extend them. These functions are also in the game mode, and they essentially just call the add piece functions that I've already shown. So this is how the path is generated. To spawn the obstacles, this is done here. So to set up the spawn points, as I said, we find the length or the size of the floor piece, and we work out how many spawn points it actually needs. So a small piece only needs 1, whereas an extra large piece will need 15. It then chooses a lane position, 1 out of 3, because the player can only move between the 3 lanes. And then it will choose a lane to spawn the item in. And then it will create an arrow component, and these spawn points are added to an array. Then in this function, it shuffles the array, chooses an item from the array. It can be either a power-up or an obstacle that is spawned. This is determined here. So there's a weighted bool with a 1% chance of being true. If it's true, it will spawn a power-up. If it's false, it will spawn an obstacle. This is so that there are less power-ups and obstacles being present in the world at one point. And these are all the obstacles that can spawn. And these are the power-ups that can spawn. So now I'm going to show how some of the quest system works. So we're in the widget blueprint of the quest board currently. The quests are structs. The structs are built off of this. It's called quest template. This is what the initial quest will be built off of. So it's a lot of strings and integers, and also an enum. So what happens is there is a map in the quest board blueprint that is a map of quest template and the enum quest category. So inside the map, you can see here are the current quests that are available. So this is the jump quest. So task string A, jump. We then have, this is the range of numbers that can be picked between. And then post string times, quest jump number of times. This is the enum. And then it's very similar for the coins. Here's the numbers. So what coins. This one has a pre-string and a post-string. So the pre-string is what will be used in the sentence to go at the beginning. So whereas jump in the jump quest is the beginning of the sentence, in coins quest, collect needs to be the first word. So that's what the pre-string's for. And then they both have a post-string to go after the number. So this happens on the new quest button. So it will get the quest map. It will pick a random entry from the map based on the length of the map. And this will be the current quest that we're looking at for now. So this, once we've gotten this quest, we break it so that we can see all of the variables. In here, this is where the number is chosen to be used in the quest. So the reason why it's so complicated is due to the difficulty weighting. So as I explained previously, the more rounds that have been completed, the harder a quest can become, which is why there's so much maths involved. There's a switch case using the round number, which is what changes the difficulty, to see how difficult the quest should be. So this is where the number is generated. Then back in here, we can see this is where the actual sentence for the text is created. So we have the pre-string at the beginning. This is for these spaces in between are for the spaces between the words. We then have task string A. So for example, for the collect coins quest, pre-string is collect, task string A would be coins. We then have the number of times, which is generated here. We then have the post string, so for the coin quest it's times. And we then have task string B. So this is just in case there would be two parts to quest. So for instance, if you needed to collect however many coins in a certain amount of time, the amount of time you needed to collect it in would be in post string B, in task string B. If the values are empty, which they are, for instance, the pre-string is empty in the jump quests, it just doesn't come up as anything. So the quest text is set, and then it's added to the UI. After this is when the player can choose to accept their quest. So if this happens, they get the quest text that's already been chosen. They know the quest. The program knows the quest that's been chosen from the map. And a new struct has to be created. So the new struct is called sQuest. It's similar to the quest template, but not the same. This is because there's an add boolean, as you can see, that says whether or not it's been completed. There's a quest text. This is a text variable, which is what is shown on the runner UI on the side so that the player can see their quest. And there's a quest type and difficulty. So this is all added into all this information is added into the new struct, and this struct is then saved to the game instance, where it will be read by the game mode when the running game restarts. So this is connected to begin play. The program will get the quest from the game instance. It will then break it, and then the quest itself, which is done in an enum, it will be put into a switch case, and then the relevant variables will be set. From here, it's quite simple. So the coin goal, you need to collect a certain number of coins. So this is an integer. Every time you collect a coin, the value of the integer will increase. And once it matches the coin goal, the quest is complete. It's all quite simple like that. The way that the rewards work is fairly similar to the quests. So all of this is on event construct. So this is when, as soon as you press on the rewards chest, all of this UI will pop up. We need the rewards to already be selected when the chest is open, because otherwise the player could just cycle through and choose whatever rewards that they want. So it's all set up. There's the left panel and the right panel, which is made up of a text block, another text block, and a button. So the text will go here, the cost will go here, and then this is the button that selects them. So the way in which the rewards are chosen is on event construct, the array of rewards will be shuffled. After that, these two functions will be called to set up the rewards on the left and on the right. These are essentially the same, they just need to be done in separate places. So how it works is, since the array has been shuffled, it's completely random every time, which means that reward L can get the first or 0th element of the array, while reward R gets the first. So they'll always be different, which is important. So once these items have been got from the array, the reward inside of them will be broken. The rewards are also made up of structs, which is here. It's called sReward. So there's a name, there's a reward type, which is an enum. There's a value, so this could be things like the score multiplier. This is how much the score will be multiplied by. A boolean say if it's available one time. So for instance, the double jump, you can't unlock that twice because it will be the same every time, so there'd be no point. And the cost, which is obviously how much the award will cost. So back in the reward chest, it breaks the struct and it creates a sentence. So back in the rewards chest, you can see this is where the quest discount will be applied. So it will take the cost of the items. It will apply the discount, which was dependent, as said previously, on whether or not the quest has been completed, and the price will be reduced based on the discount. All of the information is then reset back into a struct. Back in the event graph, we use button L as an example. Once the button is clicked, we need a way to actually purchase the reward. So here's the cost of the item. The player's coin count, if cost of the reward is more than the player's coin count, this is when they will be told that they cannot afford it. This is when the widget will appear on the screen saying that they cannot afford this item. If they can, their reward choice will be set temporarily and their coin count will be reduced. The coin count will then be reset in the game instance. Finally, once they press the select button, this is when the reward will be accepted. This is done in the game instance as well, so that it's accessible through all levels. If the reward is available one time, like for instance the double jump, it will then be removed from the array so it cannot appear in the top again. Then once it's been set, the player can go back to runner mode and it will be obtained by the player character. So it will get the rewards array from the game instance. So all of the player's rewards will go into this one array so that they're all contained. It will get this from the game instance, and for each reward they have, it will break the struct, and depending on what it is, it will go into a switch case, and then that will activate the reward. So for instance, if they have the score multiplier increase, it will increase the score multiplier. This is a function that essentially it just changes the score multiplier variable. So as they're going forwards, rather than the score increasing at the default value, it will be multiplied by the new value that they have purchased. So now I just have some final things to talk about. I'll generate another level just as I do so. So some final things to mention. There are a couple challenges faced throughout the project, particularly with the PCG generation for the decor. The reason for this is because I had to do my PCG in a slightly different way than most tutorials or most developers would expect. So the PCG graph is typically used with landscapes that you can create in landscape mode. I unfortunately was unable to use this tool in making this project because the level has to spawn forever, and that's difficult to do with the landscape mode, and it would also use so much more processing power than doing this way, which is definitely what needs to be prioritized given the amount of assets that are spawning. So how I had to do it instead was each floor piece is its own cube, and attached to it's its own actor. Attached to this is a PCG component. So I'll find the floor parent, which is here. So we have a PCG component attached to the floor piece. In this component will be a graph. So for the floor pieces, it's the coin spawner. This is how the coins can spawn and bend around the obstacles. In the decor pieces, it's the same. They have a PCG component attached to them. And in these, they will have their own graph attached to them. So for instance, the animal PCG graph, which spawns foxes on it in these zones. The PCG graph attached to it is PCGG animals. So if we go to this graph, we can see the PCG at work. So this top line, it gets the boxes that I showed previously. So these collision boxes here. And this is where it spawns the foxes. So we get the boxes. We get the normal converted density. We change all of the spawn rates of what should be spawning. And then at the end, we finally spawn an actor. These are the foxes, and they spawn on these points that have been modified from the normal of the boxes. We then have a very similar line underneath, except it spawns static meshes instead of actors. The other difference is they have a difference node, which means that this is the line that spawns the trees, and the difference node makes it so that the trees can't spawn on top of the foxes. So each decor piece is quite similar, and they all have these graphs attached to them. So this was quite a challenge at first because this isn't the usual way to use the PCG graph. So there was quite a lot of trial and error involved in getting it right. But I think it worked out quite well in the end. Other things to mention with the gameplay is as the game progresses and the player goes further along in the path, their speed will increase, which also increases the difficulty of the game. Speed increase, however, does mean that they can collect more coins. So, for instance, in endless mode, they can collect a lot more power-ups as the speed increases, but it does make it harder to avoid obstacles. And finally, one last thing to mention for the river graph, because I forgot to mention earlier, the trees avoid the path of the river. So even though the river is random and different every time, the trees always manage to avoid it. So that, for the most part, is the overview of my PCG Endless Runner. There are of course, more details in every aspect. There's a lot of work and time put into this project. There's a lot of different blueprints and graphs and assets that have been made and used to create what it has become. But yeah, this is a general overview, and I'm very pleased with how it turned out. Thank you for watching.